Now we are going to start with affine and perspective geometry. So an affine geometry means it's a parallel to the whatever we have seen. Already we have seen the part of 2D and 3D, correct? So affine and perspective geometry. Affine means it's a parallel geometry and perspective means by the view we are looking it. Okay? By the view we are looking to that particular object, how it looks like. That is perspective geometry. So that two parts we are going to see here, affine and perspective geometry. So an affine transformation is the combination of linear transformation, rotation followed by translation, reflection followed by translation, etc. So two different transformations we combine together. For affine transformation, the last column is always always 0, 0, 1, whatever the previous values, okay? The last column is always 0, 0, 1. 4 into 4 transformation matrix we have seen. So in affine transformation, the last column is always 0, 0, 1. And depending upon we are going to perform x, y and z, this value will change. These remaining values will change depending upon x, y and z coordinate that we are going to perform. Affine transformation are useful subset for bilinear transformation. To combination of linear transformation, it is useful since the product of two affine transformations are also affine. Okay, now see, both affine and perspective transformations are three-dimensional. Okay, that they are in the 3D space. And whenever we perform the transformation, it transforms from one 3D space to another 3D space. The determinant of perspective transformation is always 0. When we use the perspective transformation, the determinant is always 0. So see here, for example, these are the types or in which way it is divided. Okay. So plane geometric projection, it is divided into initially. This geometric projection, it is divided into two parallel and perspective. That is affine and perspective geometry. Simple projection, geometrical projection, it is divided into two parts, parallel, which is also known as affine, and perspective geometry. In parallel, there are three types: orthographic, axionometric, and oblique. Axiometric has trimetric, dimetric, and isometric, while oblique has two types, cavalier and cabinet. In the perspective, single point perspective geometry, 2-point and 3-point perspective geometry. So this is the categories, or it is categorized into these types, the projection geometry, initially in parallel and perspective. Again, parallel is divided into main three types, and perspective has with 3 points, single point, 2-point and 3-point perspective geometry. So that is here two types of shown here. For developing plane geometric projection, two approaches are used. One approach, the center of projection, the eye, it is shown here. The center of projection or eye point is fixed. Means suppose the object is here, the eye point is fixed, okay, and the plane, whatever this projection plane, it is always perpendicular or 90 degrees. The plane is always perpendicular and 90 degrees. And the view or the eye point is fixed. It is not changed. That is the first way to show the projection. Geometrical projection, that the center of projection or eye point is fixed and the plane of the projection is perpendicular, okay, of the viewing direction. So this is the direction in which it shows. So it is always perpendicular. That projection plane is always perpendicular to the viewing direction. That is the first way or the first approach used for this perspective geometry. The second is that the object is fixed. The object location is fixed and the viewing site or the eye, we can move from here to there. So here the second point is that the object is fixed. Whatever this object, it is fixed. The center of projection is free. The center of projection is free to move anywhere in free space. X, Y, Z directions are there. It is again the 3D X, Y, Z. And this center of projection, view, eye view, it is free to rotate anywhere or move anywhere in the 3D space. But the object is always fixed. That the plane of projection is not necessarily perpendicular to the viewing direction. Why? Because viewing direction, the center of projection is always moving. And that's why it is not necessary that projection plane is always perpendicular. It may be perpendicular or may not be. So these two methods are used for perspective geometry. The first method is that the our center of projection or the eye point is fixed. And the second method, the object is fixed and the center of projection move anywhere in the 3D space. In the first point, the projection plane is always perpendicular. In the second point, it is not necessarily perpendicular, may or may not be. So, the next one is that orthographic projection. It is the major type of it is the major type of parallel projection. Orthographic, axiometric, these are the types. Among that, orthographic projection is the major type of parallel or affine projection. Affine projection has this first type. So the simplest of parallel projection is orthographic projection. Okay, affine projection, the main or the simplest type is orthographic projection, commonly used for engineering drawing. So engineering drawing, already you have studied in first year that in the front view, top view, left view, right view, bottom view. So in these different views, we can see an object, or you have already drawn that. How the object, particular object, for example, if we consider this book. So this book, how it looks from the top, how it looks from the bottom. If I keep something here as like this, then from front, this pen will be there anywhere. If we see the bottom view, only this part and this part will be there. Correct? So top view is different. Top view, you can see only the point here. So in this way, different views are provided, and that's why it is mostly used in engineering drawing, to draw the engineering drawing. So accurately show the correct true size and shape of the single plane face of the object. Single plane face means either front view, top view, bottom view, left, right, etc. So it is show the correct true size and shape of the single plane of face of the object. So what matrix, transformation matrix is used in that case? The first, that orthographic projection are projection into one of the coordinate plane. Okay, it is projection into one of the coordinate plane, and it is again 3D, X, Y, and Z. If we want it in X plane, it is the projection in any one of the three planes. 3D, it is not possible. We see the single face. So it should be in the any one of the plane, either in the X plane, Y plane, or Z plane. So if we want the projection, this one, orthographic projection in X plane, then in that case, the matrix is like this. So the first one is for Z plane. Sorry, it is for Z plane. So Z plane, the matrix is like this. What you observe that here in this column, third column, in the third column, Z value is 0. Z value is 0 to find out the orthographic projection in the plane of Z, in which Z value is 0 and X and Y values are 1. And the last column, it is 0, 0, 0, 1. So when we multiply it with the object position vector, for example, if we consider the single point, we consider a projection vector of single point 3, 2, 1, 1. Okay, So 3, 2, 1, it is somewhere here, suppose in the XYZ plane. Multiply with this transformation matrix 1, 0, 0, 0, 0, 1, 0. Okay, we multiply this with this one. Whatever the result comes. Okay, what is the result of this? Tell me, what is the result of this? 3, 2. I write here 3, 2, 0, 1. Correct? So what is here? Only we get the value of x and y. Why? Because it is in the Z plane. Now the projection is in the Z plane. Only one face we can see here. Clear? So in the same way, if we want the projection in the x plane, then x is equal to 0. You can see here in this column, the value of x is 0. So when we multiply this with the x is equal to 0, this becomes 0 and 2, 1. Means x, y, z plane, y is 2, z is 1, and we will get the result. Means this is y and this is z. So 2, 1. Here we can see the point. If it is an object, then we can see the single face of the object. Clear to everyone? If we consider the y, then y is equal to 0, x and y. So in this case, it is 3, 0, 1, 1. So x and z. It is in which place? Y plane, where it gives the value of x and z. So in this way, we can see the single face of the object using these three transformation matrix, depending upon the plane in which we want the result to show. That is about this. The example is shown in the next PPT. That is here. This is the object given, the original object in this way. If whatever the coordinates there that is given in the book, I have not written here all the coordinates. So if all this, it is a cube. So all the 3, 4 into 8 matrix is there. Okay, for this cube. A, B, C, D, E, F, G, H, I and J. So if we multiply this and we want it in here Z plane. Okay. For Z plane, what we need to do? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. So what happens? All the Z coordinates, third column, or the Z column becomes 0. And we will get only the value of x and y. We will get only the value of x and y, and it is here, it is shown the value with only x coordinate and y coordinate. So the result is in Z plane, that is shown here. Is it clear? Similarly here, shown the result of x plane. In the result of x plane, x is equal to 0, so it shows the only y and z coordinate. No, it is x, y. It is y is equal to 0. P is y is equal to 0. Okay, so x and z plane it is shown, sorry. Y is equal to 0. That's why x and z values are there. Here, z is equal to 0. So, x and y values are there. These are x1, y1, x2, y2, x3, y3 in this way. Clear to everyone? And this is x is equal to 0. So, y and z values are there. Means it shows the single face of the object and it gives the true and the correct value if we use these three transformation matrices. Okay. So, this is another example shown here. of orthographic projection. Here it is not a single object. There is another object within the object given. So you can see here, this another object is there, as I have shown you this book along with this pen. So every top view, front view, whatever, it gives a different result. And how we get it? Using the same transformation matrix. The results are shown here. If we see it from the top, this object will appear here. Okay, and here it is cut part, correct? So it is cut here. Then rear view, this is left side view from here. This is front view, this is right side view, and this is bottom view. And it is possible to get this view. See, you have already drawn it in the graphics, engineering graphics or engineering drawing. Correct? Might be you have completed. But what you have done? You have drawn it using the paper and that pencil and everything. But it is possible to directly calculate using the transformation matrix. Once we get the value of x1, y1, x2, y2 with the particular plane, then it is very simple to draw that particular object. It is very simple to draw that particular object. So previously you have completed in your drawing, but it is with the transformation matrix. Once we multiply that transformation with matrix with our original object, it gives the result. And the last, axonometric projection. So a single orthographic projection fails to illustrate general three-dimension shape. So in axonometric, what we have seen, single face is there, either in the xy plane, yz plane, or xz plane. So it is fails to give the 3D view of a single face. So in that case, the axonometric projection is used. So axonometric projection overcomes this limitation. It shows the adjacent spaces.